Hi everyone, today we will talk about long short-term memory. Back to 1997, a single paper gave AI something it lost, a real memory. And this wasn't just some small upgrade. It was a fundamental key that would eventually unlock the door to modern conversational AI. Today, we're gonna break down the revolutionary idea behind LSTM. Let's start with a really simple question. Think about a sentence like this. The cats, which ran all over the neighborhood, are finally tired. Now you need to remember cats from earlier to choose the right verb. That's what's called a long-term dependency. And for early AI, that was a nearly impossible problem to solve. Back then, recurrent neural networks had a serious memory issue. They behaved kind of like goldfish. They could remember what just happened a second ago, but anything crucial from the distant past, it was gone. Researchers tried methods like backpropagation to help RNNs learn from earlier events, but this paper points out this massive flaw. Once the gap between cause and effect became large, the network simply couldn't link them. Their ability to learn from the past just faded away with distance. So, what was the culprit? Well, it has a name, the vanishing gradient problem. A good way to understand it is to imagine the network trying to send a message backward through time. When a network makes a mistake, it generates an error signal. This is basically a message that tells the network how to correct itself. So imagine someone at the far end of a long hallway shouting an urgent correction right there. The message is loud, it's clear, and it's strong. But as the message travels backward through time, step by step, it just gets weaker and weaker. Mathematically, what was happening is the signal was getting multiplied by a fraction of itself over and over again, shrinking it down to almost nothing. By the time the message reaches the early layers, the part of the network that really needed to learn is completely gone. The network has no idea how to adjust itself, so it just never learns those critical long-term connections. And this just nails the core issue. The author of the paper, Hawk Ryder and Schmidt Hoover, make it clear this wasn't some minor bug, it was a fundamental barrier, a wall that was preventing AI from understanding complex sequences. And this is exactly what they set to demolish.
The first idea was pretty radical. They thought, okay, if the message keeps vanishing, why don't we just build a perfect lossless pipeline to carrier? What's really cool is how they started. They actually proposed what they called a naive approach, just the proof points. They made a special memory unit with a connection to itself that had a weight of exactly 1. This creates a flawless loop where an arrow signal can just cycle indefinitely without ever decaying. It's like a perfect memory highway. They call it the constant arrow carousel. But the perfect memory that you can't control is just chaos. This naive carousel had two huge flaws. First, it was constantly being bombarded with new and often totally irrelevant information. And second, its memory was always on, always broadcasting, which could seriously disrupt what the rest of the network was trying to do. So the real question became, how do you decide what to remember and when to use that memory? And this is where the genius of LSTM comes into play.
Now we are getting into the real genius behind the long-term short-term memory. The traditional RN had a structure called the constant arrow carousel, which technically allowed the information to keep circulating, but the problem was that nothing stopped the junk information from getting in and overwriting the important memories. So what the long-term short-term memory creators did was incredibly smart. They did they did not just remove the memory loops. Instead, they built walls around it and hired a set of the very intelligent of the guards. These guards are what they call the gate units, multiplicative gate units. So at the center of the our long-term short-term memory, we still have the memory cell, but this is perfect loops. It preserves the information that for over long period. But now, all access to this cell is strictly controlled. Every read, every write, and every update must pass through one of the gates. And the clever part is, each gate is essentially a tiny neural networks whose entire job is learn how to make good decisions about the flow of the information. Let's break it down into two parts. So the first one is the input gate. Think of the bonus as a standard outside of the app club. The job is to check if the new coming information and decide is this is important enough to allow to get into the memory cell. This protects the valuable long-term memories from being overwritten by noise. Next, we have the output gate. This one is decide the information inside of the memory cell is actually relevant to what the network is doing right now. So it keeps the memory locked down tightly until it's generally needed. We're gonna crash the old guard. So that's the theory, elegant, clean, and promising. But the real question is, did it actually work? To find out, the other put the long-term short-term memories head to head against to the old RNN training method, RTRL, and the BPTT, on tasks specifically designed to break down their short-term memories, and the result was absolutely brutal. So here's the comparison. In a test where the neural networks had to remember a single piece of the information for 100 times, 100 time steps, the old method RTRL and the BPTT was completely failed, 0% success. Not even a single correct run. Long-term short-term memory, on the other hand, you absolutely nailed it. So 100% of success rate every single time. There wasn't a small improvement. It's like a totally a breakthrough. And it didn't stop here. It has to abstract original long-term short-term memory. Probably state of the long-term short-term memory could learn the time dependency of more than 100 steps. Maybe 10,000 steps at that time. So at that time, this was basically science fiction of the recurrent networks. Nothing else could even come closer. So yes, long-term short-term memory wasn't just a minor tweak. It was revolutionary leaps that finally allowed the recurrent neural networks to handle the long-term dependencies. So I'm gonna pass to the next person.
So this wasn't just some small incremental improvement. It was a revolutionary leap. Lstm fundamentally changed what was possible with any kind of data that happens in a sequence. The advantages were critical clear. As the paper lays out, Lstm was robust. It could handle noisy, messy data. It could bridge those incredibly long time gaps. It learned to generalize well, and this is the kicker. It did all of this without being ridiculously expensive to compute. It was this amazing mix of power and efficiency that made it a cornerstone of AI for the next 20 years, powering everything from Google Translate to Siri. In the end, this 1997 paper did so much more than just solve a technical problem by giving machines a reliable, controllable memory. It blew the doors wide open for AI to understand context, narrative, and the complex flow of information over time. It leaves us with a really powerful question for the future. Now that machines can remember, what can they truly learn to understand?